Hi everyone, I am Hina Wajid and I have passed my ARDMS exam with 94% marks in SPI and 94% marks in OBGYN. Now here on YouTube, I share SPI related MCQs and tips to help others pass ARDMS exam too. If you want full SPI session and all topics explanation according to ARDMS content outline and their syllabus, then you can find the link in the comments to check some of the free PDFs, some of the free videos, and you will also find details how to contact us to join our complete session.
Okay.
So, speed of sound is fastest in which material and slowest in which material?
Fastest is in bone, slowest is in air.
Okay, good. And what is exact value in air?
Air is 330. Bone, I think it's 4,000 now.
Okay, good. And what is the calibration speed in ultrasound?
I think it's about 3,900 something.
Calibration speed.
Calibration.
Speed of sound in soft tissue is?
1540 meter per second.
That is also known as calibration speed. Because
okay.
in ultrasound it is assumed that speed of sound in all soft tissues is constant, and that constant is 1.5 millimeter per microsecond, also known as calibration speed. Now what happens when speed of sound in a tissue, in a material, is less than soft tissues? For example, in fat, what happens?
Fat. So fat.
Speed of sound is slow.
It's slower.
Then soft tissue speed.
Yes. So basically, there's a chance for artifact to occur also because the echoes are going to be placed deeper than the real time.
Yes. Because
It
the
takes
speed
time
of
to come
sound
back.
is less than the soft tissue speed. What the system assumes. So that's why echoes from fat are displaced deeper. Okay, good. And what are the main factors on which speed of sound depends on?
Solely depends on medium.
Yes, medium. And which properties of the medium?
Stiffness. How hard is it to be squeezed?
Stiffness. Very good. So it is directly related to the stiffness or inversely related?
Stiffness directly related.
Okay, good. What about density?
Density is indirectly related. You gave us a formula yesterday. Speed is directly proportional to stiffness over density.
Okay, good. What about elasticity and compressibility?
Oh, okay. That one is a bit okay. Compressibility. Compressibility and elasticity is indirectly proportional.
Okay, inversely proportional to the speed. Okay, good.
Yes.
Now, our next topic is mainly about range equation and go return time. So, if we revise the pulse echo principle, what is that? This means?
Pulse echo principle is when a machine sends out a pulse All right, and waits for it to return. And based on how long does it take to come back, the depth is calculated.
Exactly. So, like in the World War, ships used sonar to detect submarines under the sea. They would send sound waves, wait for the echo, and then calculate how far away the submarine was, all by measuring the time the echo took to return. That same idea is the foundation of ultrasound. Except instead of the ocean, we send sound into the human body. Instead of the submarines, we find organs, vessels, and small structures. That's the pulse echo principle, and that's the basic of ultrasound imaging. So, what happens when we press the scan button? Transducer sends out a short pulse of sound into the body. Pulse travels through tissues, and we know when it hits an interface, a boundary. So, then what happens? Part of it bounces back as an echo, and some of the sound travels deeper. Then it also hit different interfaces and return back to us as echo. Machine measures how long it took for that echo to return. And the longer it takes, what does it mean? Structure is superficial or deeper?
It's on deeper.
Yes, deeper. And the shorter it takes, it means the more superficial is the structure. So, in ultrasound, the basis of the imaging is the pulse echo principle, as we can see here. When we send the pulse, then it interacts with the tissues and comes back as echo. Now, what is the range equation? Tasween, do you have any idea about it?
I already know about range resolution, range equation. Okay, the depth. Oh, okay, so basically what we just initially said just now lah, the depth of it is the pulse is sent out, okay, and returned back to the transducer. Okay, so basically what we want to know from range equation is just one single the distance, not go and return. So that's why we divide it by 2.
Okay, good. So the range equation is distance is equal to v, speed of the sound, multiply time, which is go return time, divided by 2. Now what is the v here?
Velocity.
Yes. And what is the value of the v?
It's the speed 1.40 meter per second.
Please repeat.
1540 meter per second.
Good. So it's 1540 meter per second, and we can also say it like 1.54 millimeter per microsecond. So machine already knows the speed of sound in soft tissue. It is fixed. Now it needs to measure which thing? Go return time. Go return time means how long the sound took to go to the structure and come back. That is go return time, T here. And why divide by 2 in this equation? Because sound travels both ways. But we need only one side time. So we divide it by 2. Speed of sound here is a constant. Go return time is also known as round trip time because it is a time to first go to the structure and then come back as an echo, both sided time. We divide it by 2 because we need only one side time. It is also known as pulse echo time. as round trip time, also known as time of the flight. All these are names for go return time. It's a time between pulse transmission and echo reception. Now what you need to remember is it takes about 13 microseconds for sound to travel 1 centimeter in soft tissues and come back again. This is our fixed co-return time, which is 13 microsecond per centimeter. To travel 1 centimeter distance, the go return time is fixed 13 microsecond. So you have to remember it on your fingertips. 13 microseconds per centimeter rule, very important for SPI. So if distance is 1 centimeter, go return time is fixed 13 microsecond. We know this thing. Now if we have to calculate go return time for 2 centimeter, how we can calculate it? Teswin.
13 plus 13, because 13 is for 1 centimeter.
Yes, 13 multiplied 2. 26 microsecond for 2 centimeter. Now if we have to calculate for 3 centimeter depth, 13 multiplied 3, 39 microsecond. 4 centimeter depth, 13 multiplied 4, 52 microsecond. 13 multiplied 5, 65 microsecond. 13 multiplied 10, 130 microsecond. 13 multiplied 20 centimeter, 260 microsecond. That is how we can calculate go return time for a given depth. So this means, what do you think? If we know about go return time, for example, go return time is 260 microsecond, we have to find depth. So can we find it?
Okay, so we divide it by 13.
Yes, exactly. Now if we have to find the depth, so we divide this given go return time with the 13 and we will give the depth. So 13, when we divide 260 by 13, answer will be 20 centimeter. So you must know about both of these conversions. When we know the depth and we find the go return time, and when we know the go return time and we have to find the depth. Very important. Okay, now next one is calibration speed. Teswin, what is the calibration speed?
Okay, so machine always assume sound travels at a fixed rate of 1.54 millimeters per microsecond. But sometimes we hit the fat, or we hit the muscle, or we hit the hair. It changes.
Okay, very good. So what happens? Ultrasound machine assume the speed of sound in the body is always 1.54 millimeter per microsecond. We call this the calibration speed. It's a constant number built into every scanner, but in reality, is this true? This we
No.
Yes.
No.
Yes, it is not true because body is not uniform. Different tissues have slightly different speeds. Fat is slower, muscle is faster, soft tissue speed is in the middle. So what happens if there is fat? The echoes will be displayed deeper because it is a slow medium. Echoes reach late, so it is displayed deep. And when there are muscles, a faster medium, when speed of sound is high as compared to soft tissues, echo are placed superficial above than their original location because they reach fast. It is known as speed error artifact or misregistration artifact. Now go return time tells us about the depth of the reflector. If there is greater go return time, for example 260 microsecond, we know that reflector is at 20 centimeter depth, and when it is 26 microsecond, it means reflector is placed at 2 centimeter. Yes. So smaller go return time mean superficial reflector, and greater go return time mean deeper reflector. And ultrasound use this principle for distance calculation, image formation, and timing the echoes from different depths. Now here are some calculations. If the go return time is 65 microsecond, what is the depth of the reflector? So how we solve this?
We always have to remember about 13 microsecond per centimeter. So if it's at 65, we divide by 13.
Exactly, 65 divided by 13. So answer will be 5 centimeter. Next one. Now go return time is 39. How deep? So simply we divide with 13. Answer will be 3 centimeter. Exactly. Next one. Go return time is 195 microsecond. So simply we will divide by 13 and we will find the depth, 15 centimeter. So understanding the range equation helps explain depth accuracy, timing artifacts, and misplacement of the structure like propagation speed error. Okay, Tasmeen, can you now summarize all of these concepts?
Alright, so basically the range equation is the distance, distance that is calculated, what do you call this? From the time the echo is sent out, okay, and until it returns back to the transducer, okay, and this is to calculate for the depth. Okay. Now, the few things that we should always keep in mind. Number one, okay, the speed. There could be a mistake of speed as what you say. We come across fat or muscle as well. Oh, okay, wait. So yeah, I didn't see a summary. I'm just talking myself. Sorry. Okay, so pulse echo principle, the depth is equals to base on echo return time. The formula is speed times go return time divided by 2. Okay, always need to remember also about calibration speed, okay, which is the speed of soft tissue, 1.54 millimeter per microseconds, 1540 meter per second in soft tissue. And always remember 13 micro, this would be, this 13 microsecond is the go return time. Alright, so sound travels 1 cm fixed at 13 microseconds. So the deeper the echo, the longer the time, the shallower the echo, the shorter the time.
Okay, good. And this is known as which equation?
Range equation.
Exactly, range equation, because it tells us about the range, the depth, the distance. And what does speed error means?
Speed error. Okay, so what it does is it assumes that all the speed is standardized to 1.54 millimeter per microsecond, but slower tissue, okay, like fat, all right, echoes may be too deep. Okay, so faster tissues like muscle, so echoes may be placed more shallow than the real ones.
Okay, good. So range equation, it helps to determine reflector depth and explain speed related artifacts. Okay, now there are questions. First one is, the range equation is used to determine
the depth of a reflector.
Exactly, depth of a reflector. The correct range equation is
B.
Yes, T is equal to C multiply time divided by 2. The 2 in the denominator of our range equation accounts for
C.
round trip travel time. The calibration speed in soft tissue is
C.
exactly. Good. The go return time represents
B.
yes, round trip time. The go return time per centimeter of depth in soft tissue is
C.
yes, 13 microsecond per centimeter. If go return time is 39 microsecond, depth
Divide by 13, 1. The B.
yes, 3 centimeter. 65 microsecond go return time corresponds to depth
65. B.
yes, 5 centimeter. If go return time is 104 microsecond, what is the depth?
Mass calculate. C.
Yes, answer is 8 centimeter. Relationship between go return time and depth is
C.
okay, good. A sound pulse travels to a depth of 10 centimeter and returns. Total distance traveled.
B.
Yes, good. B. Because sound travels to and then also comes back. So it travels to 10 centimeter but also comes back 10 centimeter. So total distance is depth multiplied to 20 centimeter. If the actual propagation speed is slower than 1.5 millimeter per microsecond, how will the echo appear?
Deeper. B.
Good, deeper. If the propagation speed is faster, how will the echo appear?
A. Shallow.
Good, too shallow. Calibration speed is stored in the machine as a
B.
yes, as a calibration speed, a fixed constant. If go return time is 130 microsecond, what is the reflected depth?
B.
Yes, good. A reflector located 20 centimeter deep will have a go return time of approximately
B.
yes, good, 260 microsecond. A system assuming 1.54 millimeter per microsecond speed will misplace echoes if
B.
yes, tissue speed differs. The range equation use which variables?
C.
Good, speed and time. 13 microsecond per centimeter rule is based on what assumption?
It's a fix. Uh, B.
Good. Speed is constant. What is the most likely artifact if propagation speed errors occur?
B.
Yes. Misregistration or speed error artifact.